Okay, we had a request to do the last part of my review from on Friday on the population genetics and calculating allele frequencies, P's and Q's in quantitative genetics. And I wanted to remind everybody that there are predator, prey, and competition YouTubes available. They're on the web, and they are announced under the announcements section on the Canvas site. So the question was, how do you calculate allele frequencies from a population that might have multiple alleles? And so this is calculating P and Q or R and S, depends how many alleles you might have. But in this case, from a slide from one of the lectures, first lecture on population genetics, I showed you how to calculate the allele frequencies. And you imagine a Petri plate with 50 individuals. They're all diploids. And so they all have two copies of an allele. And you're asking, what's the frequency of the A1 and the A2 allele? Then if you said there are 30 heterozygotes, 15 A1 homozygotes, and 5 A2 homozygotes, you could go through and count up all the A1s and A2s in this Petri plate. You could also ask what the frequency of these, and you can ask what the frequency of these genotypes are. There's a total of 15 individuals, so 30% of them are A1, 60% of them are A1, A2, and 10% of them are A2, A2, and that, of course, sums to 100%, or if you put them into frequencies, 1.0. But to calculate the allele frequencies, what we're going to want to do is multiply all of the homozygotes of some flavor, A2, A2, by, say, 2, and then sum, because they have two copies of the A2 allele, plus the number of individuals that are heterozygotes, and then divide by the total number of alleles that will be in the population. So we're now counting up alleles. So we're saying if there are 15 A1A1s, there are 30 copies of A1 alleles in those 15 individuals because they each have 2. So 2 times 15 equals 30. And then among the 30 individuals that are A1, A2, there are 30 copies of A1. So we add 2 times 15, which is 30, to 30, and that gives us a total of 60. And we know if there's 50 individuals in the population, and that makes there to be 100 alleles, that 60 alleles over 100 is a 0.6 frequency. You can do the same thing for the F2, for the A2 alleles that we symbolize by the letter Q, but you also know that if there's only 2 alleles in the population, if the frequency of A1 is 0.6, then the frequency of A2 is 0.4. So I've shrunk that example down. So now imagine that you have 100 individuals, and we're going to use the same proportion. So 10 of them are A2, A2, 60 of them are A1, A2, and 30 of them are A1, A1. We recognize these as the same ratios, so we can do the same thing. 2 times 30 now individuals that are A1, A1, because they each have 2 copies of the A1 allele in there, plus 60 of the A1, A2s, because they each have 1 copy of the A1, A2s. Those two sum to 120, but now we have 100 individuals, which means we have 200 alleles, so it's 120 over 200, also 0.6. Okay, so you can then do these kinds of problems with any number of other numbers that you were given. So imagine if you said, I said you have 100 individuals, 36 of them are heterozygotes, large A, 25 of them are heterozygotes. What's the frequency of the large A allele? Well, by subtraction, you know that you have 61 individuals of those 2 genotypes, and so the third genotype is 39 individuals of that genotype, and that the frequency of big A is going to be 36 times 2, or 72, plus 25, or 97, I guess that is, and that you have 100 individuals, so that you have 200 alleles, and so it was was it 72 plus 25, 97 divided by 200, or just under 0.5. 97, 98 divided by 2 is 44, so no, 49. So it'd be 48.5, 0.485 would be the frequency of the big A allele. 1 minus that is the frequency of the small A allele. Okay, so then the next question we have is, well, if you had some distribution of the frequencies of a genotype and you knew something about the allele frequencies, could you calculate whether it was or was not at Hardy-Weinberg equilibrium? And the answer to that is yes. But if you have just one piece of that information and not the other piece of the information, it may be hard to tell. So for example, in this butterfly example, if we knew that P is equal to 0.4 and Q is equal to 0.6, we can predict that the frequency of the genotypes is 0.36, 0.48 for heterozygotes, and 0.16 or 0.4 squared for the little a allele. If we were given these genotype frequencies, we could ask whether this is at Hardy-Weinberg equilibrium, take the square root of 0.6, take the square root of take the square root of 0.36, the square root of 0.16, get 0.6 and get 0.4, know that they sum to 1, it all works out, and we know it's at Hardy-Weinberg equilibrium. However, it could be the case where it doesn't add up to 1, those two, the frequencies of the big A and little a alleles, because you have an over or under abundance of heterozygotes in a population. And so you can then solve various problems, such as the one on this slide, where here is that problem from before, just written out as math. If you have or it's a similar problem, I guess. These kinds of gene frequencies, 0.3, 0.6, 0.1, they sum to 1. When you can ask what the expected would be from this equation. We can calculate the frequency of the A1 allele, which would be 0.3 plus 1/2 of 0.6. Or in other words, 0.6, and we can calculate the frequency of the little a allele, which is 0.1 plus half of the heterozygotes, 0.3, so that's 0.4. And so 0.6 squared is 0.36, and Q squared is 0.16, and so we end up seeing we have fewer heterozygous A1 individuals than we expect, and fewer individuals of A2. I see that there is a typo on this screen, so I'm going to pause and fix it. Okay, so there is supposed to be A2 over there. I realize that. So anyway, so this is then what you can multiply this out and get the expected genotype ratios. And here they are on that next slide, 0.36, 0.48, and 0.16. So the question here, so the answer there is that in this generation 2, you have, I guess as I said, underabundance, I meant an overabundance of homozygotes relative to the heterozygous state, which suggests that there's a selection against the heterozygous individuals, and that this is this is the opposite of heterozygote advantage. Okay, anyway, so that is a brief primer on calculating allelic frequencies from a population. And then by extension, and you should probably practice this is on some of the practice questions, is to do this with, say, 3 different alleles within a population. All right, great, thanks.